Hello, everyone. As Abhijit just said, I'm Sumedh. I'm a PhD student at the University of Southern California, and also currently a research intern with Microsoft Research, where I work on using foundation models for decision making. And today I'll be talking about two pieces of work. One, as you can probably guess, involves building foundation models for robotics, and the other basically reuses existing foundation models for robotics. This is just a slight edit from the email that probably went out to you all advertising the talk, which was basically about one of them. And I think that for completeness, it probably makes sense to talk about both. So it's basically 2 for 1 today. So whether or not you kind of believe the recent foundation model hype, it's hard to deny the successes of foundation models in the specific domains that they are deployed in. So, for example, works like the Sparks of AGI paper that came out of MSR that talks about how you could use language models to come up with LaTeX code for generating images, or truly sophisticated image generation code. For example, these stable diffusion images that are conditioned on language descriptions of the image you would like, or sophisticated chat applications, or finally, my personal favorite, sort of using language models for code generation. These sort of in their narrow domain, they are able to do some pretty impressive things. And kind of take a step back and think about how people are building these foundation models. There's maybe the three common steps to building these foundation models. And again, just to sort of be very clear, foundation models that I'm talking about are within the domain of vision and language. And so for the next few minutes, I'll talk about how people build these foundation models for vision and language, and how we can reuse them, reuse some of these ideas that they have provided to us for building foundation models for robotics. So the first step, obviously, is creating a really, really good data set. And vision and language foundation models typically have a massive, like a truly massive data set that they operate on, whether that's sort of billions of images that they're trained on, or trillions of tokens. For language data sets, they really are really, really massive. In addition, most of these data sets have some notion of labels or some notion of a quality. So the sense that given some input, you are able to map it to some another set of outputs. And finally, these data sets are extremely diverse. So they're collected on many, for example, if it's an image domain, they could be collected on various sort of type of domain, like, depending on different camera angles or lighting conditions or backgrounds. They truly contain a very large variety of domains from which this data is collected. Next, sort of very high capacity models, and specifically currently transformer architectures, which serve as sort of very good data sponges, are used to train on this data set using some sort of a notion of pre-training. And typically in language models, this happens using the sort of self-supervised next token prediction objective. And so to put it very simply, what this is doing is taking a sequence of input of tokens, for example, these inputs of like words like problems and turning, and asking the model to predict what happens next. And so in this case, it might be asking it to predict the word into, conditioned on the previous text given to it. And so if you look at the recent papers that kind of, at least in a very clear way, describe how their pre-training works, for example, Llama 2. Llama 2 is trained on 2 trillion tokens on these like publicly available data sets, and they use this sort of next token prediction objective for the self-supervised training. And once you have pre-trained on this very large data set, the goal is to sort of incorporate the kind of behavior you would like out of this model. And the way this is done is sort of this new paradigm called reinforcement learning from human feedback. And this works in a pretty interesting way. What it does is that a prompt or some kind of input is given to this foundation model. And by sampling from this language model, you can generate a few outputs that are all sort of potential answers from this large language model. And then a real human, actually annotates these outputs and ranks them, basically on the basis of which of these outputs was the most plausible, or was the most helpful, or was the most safe. And using this annotated data, we generate a reward model. And once you have access to this reward model, you can fine tune your language model using online RL. So you can actually use the language model to interact with the reward model and then try and maximize the reward model and eventually basically train your large language model to behave in the way you would like it to, i.e. behave in the way the humans who have annotated this ranked outputs would like them to behave. And so kind of to summarize, the recipe for building these foundation models is usually just pre-train on a large data set and then somehow fine-tune the kind of the model to sort of have it generate behaviors that align well with human preferences. And so the first work I'm going to present is trying to borrow these principles from language models and apply them to the domain of robotics. And try to see if we can replicate the successes of these large language models in the world of transformers, in the world of robotics. And RT1 really is sort of the most, in my head at least, is the most sort of the brute force solution, or it's kind of really just copying the idea of these large language models, but applying them to the robotic domain. And the recipe is pretty simple. The recipe basically consists of collecting a large data set of demonstrations. So basically images and action pairs of sort of optimal behaviors. And these are collected using, these are collected by robot operators who teleoperate a robot and perform sort of optimal behaviors. And this data set is collected and annotated with textual descriptions of what those behaviors look like. And then a large sort of transformer model is trained with a supervised loss on this data set. So basically you're just doing behavior cloning, but at a massive scale. And then very simply, this is applied to the same sort of downstream robotic environment that the data was collected in. And so in sort of to distill this entire idea, it's really behavior cloning, but done at a massive scale and done using language conditioning. And so the first thing to talk about, of course, is like, what does the data set that you train on look like? And the scale of RT1 is pretty massive in terms of sort of robotic data sets. It's about 130,000 trajectories. And these are all successful trajectories. So there's no negative data. There's no failure trajectories used during training. The diversity of the tasks are really large by robotic standards, but and so there's basically 700 diverse tasks that the language condition policy can execute. And as I said, again, they're all natural language conditions. So you have, in addition to the trajectory, you also have a language label that describes what that trajectory is doing. And so the table on the right here describes kind of the types of tasks that RT1 was trained on. And most of them include sort of everyday manipulation tasks within a kitchen. So interacting with objects, picking and placing them, opening drawers and placing objects into receptacles. And so in total, there were 744 tasks. And you can kind of divide them on a sort of an intuitive level into skills. And those are 8 in number. Well, once you have collected this data, the question is, how do you train on this? And I guess architecture choices are super important to get sort of the maximum performance that you can get out of these methods. And so on the right here is basically the image of how we trained this model and the architectural decisions that we made. So the first thing was basically for each of the images that you had that you get from the environment, we first stack them as you would do in as most RL works do. We stack them over 6 time steps. And you use a pre-trained efficient net, which is pre-trained on ImageNet, to encode these images. And also this efficient net is actually also film conditioned. So basically, it also takes language as input, and it's able to combine the representation from the images along with the textual description of the task into a flattened set of tokens. So there's basically the combined vision and language tokens are 81 in number. And once you have this sort of somewhat long sequence of tokens, you try and pass it to the transformer, but before you do that, you want to make sure that the length of your tokens is as short as possible. The reason you want to do this is because you would like, you're going to use the transformer in sort of an autoregressive way, and so it's going to take a previous sort of set of tokens and try and generate the next token. And so the longer your sequence, the more time you will take to generate these tokens. And we're doing sort of real world robotics, right? So we would like the sequences that we send to these transformer models to be as short as possible. And so we use a token learner, which tries and compresses each of these super long sequences into much shorter, so from 81 tokens to 8 tokens. And then after a few layers of self-attention, you spit out this 11-dimensional discrete action vector. And so parts of the action vector basically correspond to the gripper and position and orientations of the arm, and also the position and orientation of the base of the agent, so whether or not it needs to move forward to get closer to manipulate the object or not. So once you've trained on this massive data set, we try and study the task generalization of these robots. And so kind of the paradigm is basically, let's pre-train on a subset of these 744 training tasks, and then measure the performance in sort of seen tasks and also unseen tasks. And the baselines that we had to compare with are sort of these additional attempts at building foundation models for robotics. So Gato is one of the works that came out early 2022, and basically tried to combine a bunch of language and RL tasks all into one. I should correct myself. They aren't really language and RL tasks. They're language and other supervised learning tasks. So it's basically doing behavior cloning also, but across a very large variety of tasks, not just robotic tasks. And finally, also we also run our baselines on BC0, which is another sort of language conditioned generalist attempt at using transformer policies for building generalist agents. And we test on 3 types of generalizations. So one is, of course, using unseen objects. So maybe you have a set of objects that you've trained on, interacted with them, and then at test time, you're given a new set of objects. Another set of generalization dimensions is basically the distractor objects on your table. So for example, let's say that you're actually asked to interact with maybe a Coke can on the table, but you have a bunch of other objects on the table, and the hope is that the agent can still manage to manipulate that object correctly in spite of the clutter around it. And finally, a somewhat harder generalization problem, which is kind of being able to generalize regardless of the background and the tabletop surfaces. So if you change the layout of the tabletop, or if you change what the background looks like, is the model still robust to these variations? And we find that RT1 is actually somewhat robust to these distractions and to these perturbations in the environment. And so in comparison to the baselines, it's able to still perform its task with relatively high success. So 97 is on the seen tasks, but in spite of variations in backgrounds and looking at new objects, it's still able to somewhat satisfactorily manipulate these objects. And I guess the biggest drop in performance is robustness to backgrounds, which is what we found it was most sensitive to the variations in background and tabletop surfaces. We then checked how well this model performs when you generalize to new scenes. And so the way we did this was basically to try and change a lot about the environment that the agent was trained in. So one was basically trying to change the basic lighting conditions and the counter layouts, somewhat common if you were to try and deploy policies like this in the real world, right? So if you could have a different layout of the kitchen or change kind of the lighting conditions of the kitchen, then could the robot still do its task? The next level of generalization is kind of change what kinds of distractor objects were available to it. Also a somewhat reasonable assumption, imagine if I try and deploy the robot in my kitchen, the kinds of things I might have in my kitchen would be very different from the ones it was trained on. And finally, try and change the entire layout, or try and change the complete environment in which you're deploying the policy. So for example, the policy was fully trained on tabletop surfaces, but what if we placed the robot near a sink? What would happen then? And we've basically found that RT1 does better than existing methods, but does suffer from like appreciable reduction in performance when you have these sort of hard generalization problems. So like task success sort of somewhat falls significantly from 97 to 50 now, when you do have these hard generalization problems of completely different environments. And so definitely we're not there all the way, but as you can see, like there is still sort of a significant amount of work to be done to improve these numbers to have these policies be truly generalizable. Next, we also studied sort of sim to real generalization. So we had a simulation kitchen environment that we could collect data from. And the question was, can we mix these data sources? Like, is it possible to train both on simulation data and real data? And does this at all hurt performance? Or does it, or can you still get away with training on these multiple different data sources? And what we found is basically that if you add simulation data, the performance in real only decreases somewhat, so about 2% in terms of task success, but you're able to get a significant bump up in sim performance. So basically training only on simulation data is going to provide an X amount of performance, but basically adding simulation data will allow you to improve performance in simulation as well. So in the kind of takeaway from this is that RT1 is a really good data sponge, and it's able to like combine data from various different data sources and still generalize across these different, I guess, environments without affecting performance appreciably in any one of them. So basically no degradation, but improvement in simulation. Finally, we also tested whether or not we're able to do embodiment generalization. So right now we've only talked about a single robot demonstrations. What if we had two different robots that you could train, that you had data for? Could you train one model that that can absorb this data and still have high performance? And so we had two separate setups. One was this everyday robots robotic embodiment, which is basically a mobile manipulator. So we had a base that could move, an arm that could interact with objects, and a head-mounted camera. And we also had a KUKA robot, which is basically a robot that was used to collect and separate trash into recyclables and compostables and so on. And so what if we had data from these various data sources? Could we combine them into a single robot with different embodiments? And what we did basically find was if you trained on everyday robots data only, of course, you had not a great performance in KUKA, but by combining these models, you don't actually suffer from a lot of performance drop in the EDR setup, but you actually gain quite a bit in the KUKA setup as well. And so again, kind of the takeaway here is in spite of having different embodiments, you're still able to combine data sets and combine data from different embodiments and get pretty good performance. The last thing is basically we did some ablations on how much the size and distribution of training data affects performance. And we found that, of course, this is like the size and diversity of data is super crucial. And so we had sort of two axes of variations. So one is basically how much of the total data do you actually use to train on? And the other axis of variation is basically how much of the tasks do you actually use? And kind of the takeaway from the plot on the right here is that, of course, kind of reducing the data size to a fifth also results in a performance drop to about a fifth. So, using about 20% of the data means you get 20% task success. And a similar sort of similar kind of finding we found is basically if you reduce the number of tasks by 25%, you get about half the performance. And so definitely like reducing the number of training tasks and reducing the amount of training data definitely does hurt RT1. Great. So to go back to our recipe of foundation models, can we critique this recipe and can we critique RT1 from this lens of the foundation model recipe? And so the first thing that we found is, RT1 needs a lot of data, right? It needs 130,000 trajectories. And while that seems small by like machine learning standards, it's still super expensive to collect this data. So we had to collect this data over a year of basically robot operators teleoperating the robot and collecting demonstrations, one by one for each task. And yeah, as I said, you need experts. And so this entire endeavor is super expensive. And finally, the demonstrations aren't very naturalistic, right? The only way to gather a useful demonstration is to actually control the robot and get it to do the task. You cannot use human demonstrations. And in an ideal world, you would like to show the robot, maybe in your own kitchen, about what it should do. And the hope is that maybe the robot can utilize this data to learn how to do a task. And this is currently not possible with RT1. And finally, RT1 basically assumes access to only expert demonstrations, right? It doesn't actually use any explicit reward. And so there's really no fine-tuning mechanism here, right? And so can we, so if you kind of go over these individual challenges, as I mentioned, like collecting data is definitely very, very difficult, right? And people have made some attempts at doing this, right? You have this Berkeley Bridge data set, you have RoboNet. And as I said, to kind of mimic those scales of internet scale of training data that you have for images and for text, we're not quite there yet, right? For this reason, because collecting robot data is expensive. Finally, also collecting bad data is possible, right? You can just have a robot do random stuff in the environment. But of course, you suffer from safety issues. And obviously, it's hard to learn from that data. Whereas collecting good data requires sort of human intervention, which is expensive. And finally, collecting data requires you to have collecting generalizable data requires you to have a variety of domains and sources, right? So maybe you might have to have different robotic embodiments, have a bunch of different tasks, or have sort of multiple variations of the same object with different kind of visual appearances for these models to generalize, right? And this is difficult for real world robotics. Sorry, is there a question? Okay, maybe not. Additionally, there are also some challenges for coming up with reward functions for these models, right? Like RT1 doesn't need a reward function because it's using expert data. But let's say that you had to have this Boston Dynamics mule pick up these boxes, and you want to write a reward function to tune that behavior. What you would ideally need is kind of the height of this object off the ground, right? And this is difficult to obtain, right? Like in a real world setting, how do you actually measure this height? If you have a computer vision setup that's sort of brittle to distribution shifts. And so to define sort of really good feedback mechanisms, you need to have some knowledge of the state of the environment, right? And this is a pretty strong assumption to make in sort of real life robotics. And also, of course, if you're going to do this fine tuning, you need experts to write these reward functions. So basically, some grad student needs to come up with a perfectly mathematical way to encode this behavior in a reward function and hope this works. And again, the same situations of diversity also hold here, right? Like, what if I just switch off one of these lights here? And if I have a computer vision setup trying to estimate this height, good luck getting it to generalize. And so these significant challenges exist when you build robotic foundation models. And what I'm going to talk about next is a method to try and alleviate some of these challenges. So let's kind of enlist what we would like robotic foundation models to be able to do, right? First of all, we would like to have methods that require very little data, right? Not 130,000 trajectories. How about one demonstration? And maybe one demonstration that anyone can generate. So maybe you can, a demonstration in the form of language, right? Telling the robot what you want it to do. Or by showing the robot what you want it to do, right? Maybe it's like a single video demonstration. And ideally, you would like it to be actionless, right? You don't actually ever, when you watch a YouTube video about how to do a task, you don't actually have action signals for that. You just have a video demonstration. And finally, can we use more naturalistic ways to train these robots, right? Can we learn by watching unstructured videos in environments that are not the same as the robotic environment? And so The work that I present next is sort of an attempt at trying to do that. Like, can we use, I meant to say, can we use data collected in kitchens like this from a human and transfer to robotic kitchens like this? And so the next bit of work is basically what was advertised to you, which is RoboCLIP, where we work to show how to use a single demonstration, a video demonstration, or a textual description of a task to learn robot policies. The way this is done is kind of using this really powerful idea that people have been utilizing in language and image pre-training. And so CLIP, which I'm sure most of you are familiar with if you work in machine learning, is a really nice idea of trying to encode images and text, or basically two sort of inputs from different domains into the same or a similar latent space, and try and align them in the same direction. So imagine that you have images like this image of a dog and a label describing what that image is. What you try and do is you try and encode it into a latent space, and then take the inner product of these two vectors that you have encoded, one from the image and one from the language, and you try and align them during training. And basically what you've done is basically aligned vectors that have semantic meaning along the same directions. And this idea is pretty powerful, right? And it also is generalizable to not just static images. You could do something much more clever, right? You could also encode videos. So you could have this video of Gordon Ramsay yelling, and then kind of what he's yelling, and try and encode them into the same latent space. And we hypothesize that these models contain a lot of rich dynamics information. And not to mention, they're also semantically aligned, right? So they know what dynamics looks like, what a task looks like. So for example, they have information about what might entail picking up an object, because they've seen videos of humans picking up objects along with semantic labels that describe how to pick up objects. And not to mention, and I think this is the most crucial thing, they're trained on a very, very diverse data set, right? They're trained on a variety of like videos with sort of randomized backgrounds, or multiple different actors that look different, or have sort of differences in visual appearances of objects that are interacting with, kind of the things that we want our robotic foundation models to generalize to. And so our hypothesis, sort of clearly stated, is that we want to use these models that are pre-trained on these video data sets to try and somehow use them to generate robotic policies. And the hope is, because of this sort of large-scale training, they already contain enough information to teach robots how to do things. And the idea is really simple. Let's take a pre-trained video clip model. And so it consists of an image, basically a video encoder, and a textual encoder of what's happening. And what you do is you provide an image, provide a video of the robot interacting with the environment, and maybe a textual description of the task you care about. And you encode both of them into the same latent space using these pre-trained models. And then you utilize the similarity score between these two modalities as a reward for the agent, right? So in a sense, if the video of the agent interacting in its world is actually, maybe if it's a successful trajectory of the robot opening the drawer, then the video will encode, will have a high similarity with the text of robot opening green drawer. And so the RoboCLIP reward is basically just that. Can we utilize the sort of, so basically the idea is you have an environment that provides you sort of a state, which is given to the policy. And obviously the policy spits out an action, which you apply to the environment. And of course, this loop continues on for every time step. At the end of an episode, you collect a video of the interactions of the agent in the environment, and you encode it using the pre-trained video encoder from these video clip models. And then you utilize maybe an expert demonstration of how to do that task in terms of a video, or a textual description of what you would like the robot to do. And you use this pre-trained clip model to generate a latent vector that sort of encodes this descriptor, this task descriptor. And then you do what all of these people do is you calculate the similarity score between the episode of interaction and the task description, and you obtain a scalar. And that's basically the reward that you get for the entire episode. And of course, this outer loop sort of happens at the end of every episode. So how does this kind of link back to what I spoke about, right? You now have an algorithm that requires very little data, right? Because you can use one video demonstration to condition your reward. You could also talk to the robot, right? So you can tell it what to do by speaking in language, or you can show it what to do using a single sort of video demonstration, right? Maybe you could have in this, let me just go back to the slide here. Instead, you could have, instead of a video demonstration of the robot doing something, you could just have a human doing the same task. And you can encode it and use that to generate rewards. And so we study how, this algorithm, this RoboCLIP algorithm, how does it behave? And so the setup is pretty simple. We pre-train on the RoboCLIP reward, and then just do inference in the downstream robotic environment. And so what you see here is RoboCLIP text and RoboCLIP video. Those are our approaches. And what they are basically rewards that are generated using, so they are basically the performance of the agent when pre-trained on the RoboCLIP reward, conditioned on an expert demonstration of the video of the agent interacting in the environment, or alternatively, the agent that is generated after pre-training on the RoboCLIP reward that is conditioned on the textual description of the task. So, for example, in the robot closing the box environment in MetaWorld, robot closing the door environment, when you prompt it with robot closing box, you get some reward function, and you use that to train your agent. And so we find that we're actually able to get the agent to actually converge and generate really high fidelity trajectories in the environment just by pre-training using like a pre-trained CLIP model. And the baselines here are basically other imitation learning algorithms. And crucially, these are actually imitation learning algorithms that use both states and actions, whereas our method doesn't actually use any actions, right? Like the demonstration is only just a video. And so basically the point of saying that is that you actually have these competing methods have more information than our methods, and we're still able to sort of outperform them because of the power of these like pre-trained foundation models. So here are some examples of the recovered trajectory. So when you condition on the text of robot pushing a red button, this is the resultant trajectory that you get. Or alternatively, here's a trajectory of the robot closing a green drawer when conditioned on this language input, or sort of robot opening black box. And so the point is you can get sort of very nice reward functions by using these pre-trained models for reward for basically learning a task. We also studied how you could use OOD videos to generate rewards. So at the bottom here are the GIFs that I used to condition the video model and as a demonstration. And we find that in each of these environments, we're able to get the policy to like almost complete the task using these out of domain videos as a demonstration. So here's some examples of that. So the robot basically tries and interacts with the red button and moves closer to it. So in this video, I guess it fails, but we're able to find that like this is, if not already complete the task, but it's a good initialization for a policy to interact with the world. Another example is this drawer opening task, and another for the robot opening the black box. The other really interesting result that we sort of recovered when playing with these models is basically the ability to style transfer. So on the left is a demonstration video that we provided to the agent. And on the right is the resultant policy that the agent recovered by pre-training on the reward generated by the demonstration video. And what you can kind of see is that there's a nice sort of style transfer across the demonstration video and the resultant video. Here's another example of that. You have this like demonstration video that has this nice arc motion of quickly opening the door, and the resultant policy somewhat tries to mimic that, misses, but then tries to recover from there. And so what you can do is also have these like styles that you can get from your demonstration video distilled into the downstream policy by using this pre-trained reward, which is of course really hard to do. So for example, if I was asked to write as a grad student, asked to write a reward function to have my robot behave in this certain way, That's really difficult. I don't think intuitively there's a way to do that. But you can use this pre-trained model, show it this demonstration, and voila, you have this reward function that allows you to recover that style of the policy. And so, kind of going back, we've discussed this algorithm that requires very little data, so just the order of one demonstration. And most importantly, anyone can teach the robot using this algorithm, right? You don't need sophisticated reward engineering. You just show it what you want it to do, or tell it what you would like to happen, and then the robot can learn off of this reward function. And finally, and most importantly, you can now use basically a lot of unstructured data, maybe data from YouTube, or sort of data from human demonstrations in environments separate from the downstream robotic environment, and use that to learn policies. So I guess in summary, we talked about two main approaches, I guess. The first was this sort of way to try and build robotic foundation models, right? The question was, how can we sort of build on these advances in language and vision models and train very large-scale robotic models that are trained on a large data set of demonstrations. And the idea was really simple, right? Let's just supervise, learn these expert behaviors, and you have a somewhat competent policy. And then the flip side to it was, can we use existing foundation models, and then because of their pre-training, they contain sort of this rich dynamics information and also semantic information, and can we kind of harness the power of these pre-trained foundation models to train robots to do sort of these somewhat difficult manipulation tasks. I just want to thank everyone at USC, my advisor, Professor Laurent Titi, and my co-advisor, Professor Erdem Beek, along with our fantastic collaborators on RoboCLIP, folks at Stanford and at Google Brain. Thank you so much for listening to me. I think I have finished. If there are any questions, I'm happy to take them now.
Yeah, go ahead, just shout it out, Russell.
You just shout it out?
Yeah, just shout it out.
It's a great talk, very interesting material. How complicated can this task be? For example, if you wanted to learn about putting A on top of B, but B wasn't clear, you have to then clear it all. Can you do like strip style planning, or is it just? That's the question.
Oh, great question. So I think how complicated can they be? We were able to get these policies to work in Franca, the kitchen environment, and also in Meta World. The main issue I think that I found was that the model is, as I said, the model is fully pre-trained only on human data. So we don't actually use any robot videos to fine tune the model. And so sort of domain overlap is super important. So for example, let's say that you have a new environment where the overlap between that environment and those human demonstrations you had was very low, then this model kind of fails there. You could also imagine using a planner, as you said. So we had some experiments. So this paper will be out on arXiv maybe in the next 2 or 3 weeks. We have some experiments on using a planner. So instead of using a policy, just generate a plan, apply that to the environment, and then kind of use the resultant video as a reward, and then replan every few steps, basically. And the reason that's not the main focus is because I think for this method to be sort of useful, I think you need to have a reactive policy. Whereas it's unclear whether just using planners would work, at least to me. But my thinking is the biggest bottleneck for task complexity, I think, is domain overlap. Yeah, I'm not sure if that answers your question. Does it answer your question? I hope.
Pretty much, but I still think when the plan involves, what if the action requires addressing preconditions? I grew up in the day of strips planning, you have to solve problem A to do problem B. In the environment, you might see the robot doing some of these actions that have prerequisites, or is that just a whole different topic?
Yeah, I'm not fully sure I get the preconditions issue. So could you give me an example of like where you think something like this would like maybe the precondition is like off camera or something? Is that kind of what it is? Like maybe
The canonical example is, put the pencil on top of the box.
Mhm.
The box already full of stuff. I've got to clear the box off first. So to be able to put the pencil in the box, I've got to have a clear box top. And already there's a green cube on it. I got to put a green cube on. So this is the standards which mentioned strips from way back when that was.
yeah. I mean, I think in terms of these preconditions, like it's possible that like thinking off the top of my head right now, I think if you don't have like a way to capture visually that precondition, then maybe that reward function is poor, right? For example, like maybe you need a precondition and that happened off camera when generating the reward function, and maybe during test time you don't actually see basically during test time you don't have access to that precondition from the visual point of view, or maybe there's some kind of like partial observability where like through the camera you can't really see it, and so then in that case I guess the reward function would be poor. Yeah, that's what I think. That's maybe where like that kind of, yeah. Mm-hmm.
Any other questions? Yeah, go ahead.
Yeah, I guess to follow up with that question, in meta world, are there environments, for example, where you have to like open the drawer and then put a block in the drawer? Are there like those types of environments that involve two different skills instead of like just open the drawer or just push the button?
So that's a good question. So I don't think that like the custom the stock meta world that you have has like a skill chaining type situation. But like the only task I can think of is basically like where you have like two receptacles and you have to place one object from one to the other. But I don't think there's like a skill chaining situation. Yeah. So I don't think we haven't tried that, but I would be interested in seeing like how far you could, like what would be the length of the task, at which point doing this video reward breaks. But yeah. Sorry, can you guys hear me?
Great, any other questions? Thanks so much.
Great, thank you so much. Thanks for having me.